All right, welcome back. This is the second part of gravity and motion, and this is Lecture P in the Natural Science 102 course here at Danville Community College, spring 2022. Gravity and motion are so interlinked. You're going to see me talk about motion, then gravity, then motion back again. So the two concepts really can't be divided and split into two equal lectures. So this lecture is going to have more on motion. All right, so let's talk about falling objects. Remember, Aristotle, way back 400 BC or so, thought that heavier objects are going to fall faster and lighter objects are going to fall slower. The Leaning Tower of Pisa is in Italy, and it's a great area that you can drop objects because it's away from the building. So if you drop objects from the top floor, they'll be sufficiently far away from the building that not bump into windows or something, okay? And Galileo reportedly dropped two objects, one heavy, one light, but they were the same material, like lead balls or iron balls. And observers down the bottom reported that they fell at approximately the same time. So this refuted Aristotle's ideas that heavier objects fell faster than lighter objects. He was able to measure the time that it took for the objects to fall, and he found that the distance covered is proportional to the square of the time of the fall, okay? So we'll talk more about that in a bit. So what this basically means is that objects are accelerating, okay? They are accelerating. And we've already talked about acceleration before, okay? So in English units, let's just go with English units, the acceleration is 32 feet per second, okay? Okay, so 32 feet per second could be written as this mathematical ratio. We have a square here. Don't worry too much about this, okay, this representation. Let me just draw a picture and try to explain this in more simple terms without too much math, okay? So, let's say you're on a tall skyscraper, okay? And you have one of these balls, and you want to repeat the experiment that Galileo did back in 1600s in Italy, where he dropped an iron ball or something like that from the top of a skyscraper, the Leaning Tower of Pisa back then. I think it's 400 or 500 feet tall or something. But anyway, a skyscraper could be many hundreds of feet, right, depending on how you are, okay? So what you do is you have a little iron ball, and so that's your object, and the time is equal to 0. Okay, you start your stopwatch. Okay, so ready, set, go. You drop the ball, you hit the stopwatch. After 1 second, the ball will have traveled 32 feet. Let me So S is an abbreviation for seconds. All right, here's the ground down here. 32 feet is about the height of a 4-story building. So over here, Sova Health, Danville Regional, I think is about 4 or 5 stories. So if you were to take an object, please don't do this, but if you were to drop your car keys out the window of the 4th floor hospital room, it would take 1 second, boom, it would hit the ground in 1 second. All right, and that's 32 feet. All right, 1 more second would be double that. So time, let me try to make these about equal. Okay, so time is equal to 2 seconds, okay? the object that you're dropping here, the iron ball, is going to travel 64 feet. So it's moving faster now, okay? Here, the object traveled 32 feet in 1 second, okay? So that's pretty quick. And after 2 seconds, it's traveled twice as much, okay? And then after time is equal to 3 seconds, it's gonna be 4 times that. It's off the chart. I think maybe it's on the ground here. So what's 64 times 2? That's 128, right? 128 feet. So it's not linear, okay? In 1 second, you go 32 feet, okay? I forgot, this color doesn't show up well on the camera. So let me switch. So let's take all of this data and add it up now. So the distance is 32 feet after 1 second. Okay. So in 1 second time, if you drop an object out of an airplane, it will travel 32 feet. Not that far. I mean, that's like, you know, a few steps, okay? But in a total time of 2 seconds, it's going to be 32 plus 64 feet, right? Okay, because the object is speeding up. I don't want to do that on my calculator. And then the third second, we'll use, I don't know, gray here. The third second, it's going to travel 32 plus 64 plus 128. So those are quite large numbers. I think maybe will do it on my calculator just so you can see this. Okay, so that's 32 feet, 32 and 64. Yeah, I know you could do this in your head pretty easily. I'm just gonna do it this way anyway. So this is 224 feet, okay? So the object is every second going 32 feet per second faster, okay? Here it's going 32 feet per second, then it's 64 feet per second, then 128 feet per second. And of course, we know if we drop an object from a very high height, it's going to be moving very sufficiently fast to you know, do some damage to somebody or a car or something down on the ground floor of a parking lot, okay? So this is the acceleration of gravity, okay? You're going from 32, double that, 64, double that, 128. So every second, you're going twice as fast, twice as fast, twice as fast, okay? So that's the acceleration due to gravity. Now, I saw this. I don't want to put this video on my YouTube lecture because I'll be flagged on YouTube for a copyright violation. But it was an awesome video by Mythbusters, and it was similar to this experiment I will show you here. Okay. So if you have an archer, letting go of an arrow that's shot through a bow, it's eventually going to strike the ground. At a certain time period, because the arrow, in addition to moving through the air this way, okay, is being accelerated by gravity and is falling to the ground, okay? Sorry, that's not very flat on my drawing here. Now, if you have another person over here, let's say, that just takes an arrow in their hand and drops it, it will fall to the ground and hit the ground after a certain time, okay? And what Mythbusters did was they fired a gun from, fired a bullet from a handgun, okay? and then they had a robotically operated, release thing that exactly timed it at the exact moment. So the exact moment that the gun was fired, over here, a little lever dropped just a bullet. And what happened was, this bullet flew through the air about 300 feet down like a warehouse, but it eventually hit the ground because of the force of gravity, the acceleration of gravity bringing it down. And this bullet was just dropped, like you would drop a pencil to the ground. And these two hit the ground at exactly the same moment, okay, which was quite amazing. They caught it on high-speed camera, the bullet going through the air, and then the one came into the frame, and they both hit the ground at the same time, within like 1 foot or something, wherever the camera was pointing on the ground. Okay, so this object is falling, even though it's been shot out of a bow, and an arrow just by itself is dropping because it's being dropped. Okay, so it doesn't matter if you have a horizontal projectile with horizontal velocity. Okay, the vertical velocity of the arrow is caused, vertical means up and down, the vertical velocity of the arrow is caused by the force of gravity, just like you could take an arrow and drop it in your hand. Okay, so if you had a bullet and you wanted to know how long it takes for it to hit the ground, you could just drop it and try to see how many, fraction of a second it would take to hit the ground, and that's how, long it would take for the bullet eventually to be pulled down towards the earth and hit the ground. Okay. There's all kinds of mathematical formulas for the distance and the shape of this curve and everything, but I'm not going to get into that right now, okay? Ever in this class, okay? All right. Let's talk about the 3 laws of motion before we talk a little bit more about gravity, okay? These laws of motion were formulated by Newton, but are kind of a piggyback on Galileo. The first law, an object remains at rest unless it experiences a force. And we've talked about that before, okay, in the previous lecture. A parked car is expected to be a parked car unless somebody's driving it or unless something's pushing it, right? Number 2, an object in motion generally remains in motion. We've already talked about that, okay? A satellite out in outer space is just going to keep orbiting because there's no force being put on that satellite. Number 3, for every force, there's an equal and opposite force. And so there's a lot of philosophy behind this. Those of you in philosophy class know that, or ethics or whatever, there's good and bad, good and evil. Star Wars, you've got the dark force, the good force, and so on. Well, actually in physics, for every force, there's an equal and opposite force. Let me illustrate for you this, maybe with this water bottle. If I hold this out for a long time, my arm starts getting tired. Gosh, it's starting to hurt my arm. I'm starting to become uncomfortable holding this water bottle out at a large distance like this. What's going on here? Well, gravity is pulling down. I can feel it. It's like somebody's pushing on it. It's like somebody's pushing on it on purpose. That's gravity, the force of gravity. Now, to keep this object here, I have to use my muscles, biochemical energy, to make my muscles try to push in the opposite direction, okay? If I put it on the countertop, don't think you can see it here in the video, barely. If I put it on the countertop, it's not moving either, okay? gravity is still gravity here on planet Earth. It's still pulling it down. That's what we call weight. We'll talk about mass and weight in a bit, but the ground is pushing it up, okay? Now, if you're mad, don't do this, please, but if you're mad and you punch the wall, you hurt your hand. It feels like the wall has hit your hand, or the wall has actually punched you, and that's exactly correct, okay? We normally think, well, our hand is in motion, the wall's not moving, boom, I hit the wall. Ouch, that hurt my hand, right? But you could experience the same amount of pain if you just keep your fist like this, don't move it, and your friend takes a board and smashes it against your hand, okay? You're gonna feel the same amount of pain. You know those video clips where you've seen a karate guy, you know, punch their hand through a board? Well, they could just hold their fist out like that, and somebody else could take a board and hit them really hard, and it could smash. And you've probably seen videos, maybe Jackie Chan or other action videos, movies where, you know, somebody has a board and they hit somebody over the head with the board, and the board breaks in half, right? And you've probably seen karate films or, you know, a TikTok video or something where somebody smashes their head into a board and the board breaks. So for every force, there's an equal and opposite force, okay? Forces always come in pairs, okay? Forces always come in pairs. All right, so those are the 3 laws of motion set forth by Isaac Newton, and some of them are very similar to Galileo, and some of them are an extension, okay? We've talked about the first 2 in great detail. We haven't talked too much about this 3rd law, so I'll give you some examples, I guess, of that. And then we'll come back to weight and mass, which is related to the 3rd force, I guess, okay? So Newton's 3rd laws is related to forces. For every force, there's an equal and opposite force, and things balance, okay? Whenever you put a force on an object, it begins moving, okay? It begins moving, accelerating, and speeding up. And, where am I? Oh, yeah. So, yeah. So, let's say, here's a skateboard, all right? And we have a pitcher, somebody that can throw a baseball very, very, very fast. Okay, so they throw a baseball like 85 miles per hour through the air, that way, okay? What's going to happen? Okay, well, when they put a force on the baseball to cause it to fly through the air with such velocity, the ball is putting a force back on them, okay? And since we have wheels here on the skateboard will begin going backwards, okay? My high school physics teacher told me a story about one of the baseball players that was very athletic and could keep his balance while doing this, and he had a bucket of, I think, tennis balls or something. And he was standing on a skateboard, and he grabbed the tennis balls and he threw them through the air, one by one by one by one, and he started speeding up his skateboard in a backwards fashion as he was doing that, okay? So you put a force in that direction as the arrow is written to get the ball moving, but the ball, at the moment the ball is leaving that person's hand, is putting a small backwards force equal in magnitude, equal but opposite to that force that you put on the ball, okay? So this white arrow represents the force that you put on the ball to make it fly through the air. And in blue here, that's the force put on the hand. Okay. And as a result of this experiment, the balls fly to the right. I guess plural if you have more of them. and the skateboard and your body begin to move to the left. Those of you into firearms know this. If you fire a gun, you have the recoil, okay? The bullet is pushing, your gunpowder and everything else expanding, and gases and heat are putting a force on a bullet to make it move from 0 speed to very fast going in this direction, okay? And when that happens, that same action puts a force backwards on the gun, and you feel a recoil, right, as you fire a gun. So here's a bullet. Okay. You're putting a force to make the bullet fly that way, to the right, and you have a recoil force on the gun. We call that recoil. And these forces are equal and opposite. There are many different types of experiences that you may have experienced, but I won't go through many more examples. I think you have the idea. One of the interesting things, if you've ever seen space movies, is when you have an astronaut they're kind of floating out there unless they're tied on with a rope that they could pull to get each other closer, or stand on something or grasp something. They're pretty much just floating in outer space, right? There's not a whole lot they can do, okay? But if you have two astronauts close to each other, and there's a, okay, I'm gonna use a little dorky, cartoon here for my rocket, okay? Let's say these two astronauts are floating here in outer space, and they want to get back to their rocket ship to go back home. There is a way to get one of these astronauts here, but there's no way to get both of them here. They're going to have to make a decision who's going to sacrifice themselves, okay? This person here on the left, with their space helmet on and spacesuit on, could push on the other astronaut. If they pushed on the other astronaut, okay, astronaut B would float to the right. Hopefully they make it to a handhold and, get in the airlock and fly home safe, okay? But what's gonna happen to astronaut A? As they put all this force onto the astronaut B to get them moving towards the ship, they themselves are going to be pushed backwards, and they're going to float off into outer space and be lost forever. Again, we're in outer space. Here's the Earth, there's stars, whatever. Okay, you get the idea. So that's a critical situation. Okay, if ever two people have lost their tether, normally there's ropes or whatever locked onto people, and if they're stuck, they're just floating out there. If there are two people, they have a chance to survive. But if there's only one person, you can't swim or anything like in the Bugs Bunny films, okay? All right, so for every force, there's an equal and opposite force. All right, so let's talk about weight and mass. Now, if you have a block of material that's 100 kilograms, that's about 200 pounds, by the way. So that's pretty heavy. Now, if you have a 200-pound object here on Earth, it's going to register on a digital scale, maybe at the post office or something, and say, 200 pounds. Okay? Here's your scale, digital scale. Okay? And the reason why is because you have a force from gravity pushing down on the block, and therefore the balance registers that force through electronics and all that to give you the weight. Okay, so this is weight. Weight is the amount of force imparted on an object in gravity. That's a key concept, so I've highlighted it here on the slide. Weight is the amount of force imparted on an object due to gravity. If this is Earth, this object is going to weigh 200 pounds. If you're on the moon, it's going to weigh, I forget what the numbers are, 1/3 or 1/6 as heavy. Okay, it's going to be lightweight. Okay. If you're in outer space, like floating in outer space somewhere, even in orbit around Earth, and you would have a balance, and then you would have an object on there, the two would just be floating. They would not be held down. There's no gravity, so it's weightless. Okay, so outer space, for example, on the International Space Station, this 200-pound block of lead, which I'm saying is 100 kilograms, okay, is going to be weightless. Okay. There are different ways to experience weightless. If you're in an elevator, okay, hopefully this doesn't happen, but the cable that's lowering you to the ground, if it snaps and you're suddenly in free fall, you're going to be weightless. So here's your elevator that's failed and falling through the air at high speeds. If you do skydiving, all right, and you jump out of an airplane before you pull your parachute and you're just falling through the air, that's free fall. If you're on a bridge and you're bungee jumping off a bridge, you're in free fall. So all of these, you're temporarily weightless. Okay, you don't have to go to outer space to be weightless. You could jump off of a diving board, okay, and you're momentarily weightless. You could go skydiving, for example, and you're going to be weightless. All right. Mass is the quantity of matter and remains constant. So it doesn't matter if you're on the moon, the International Space Station, or Jupiter, the 100 kilogram block is still going to weigh 100 kilograms. Okay, so that's the difference between mass and weight. Weight is the apparent, is the force on gravity. Weight is actually a force. Mass is actually a quantity of material. Okay? So if you want to lose weight, you can go to the International Space Station, and yes, you'll weigh nothing, but you're still going to have the same body mass. You're still going to be the same person with the same amount of material. Okay? Let's talk about, where did that go? 39. Okay, yeah. So we talked about mass, weight. I was going to talk about, mass and weight here. We talked about that. Every force is an equal opposite force. Okay, so what is the law of gravity? Now, gravity is one of those four fundamental forces. We don't really understand it, okay? but we know that any two objects with mass are attracted to each other. So if I took two pencils and I put them out in outer space, very carefully positioned them with zero velocity, zero speed, and they were like, you know, a foot apart from each other, okay? I could, you know, set up a camera too, way over there or something, or a telescope or something far, far, far away that doesn't affect the experiment. And these two objects would be attracted to each other. And over a period of months and years and so on, they would eventually, you know, you would come back to the area where you place these two pencils and they would actually be stuck together. Like, wait, what happened? How did they attract one another? Well, it's the force of gravity. We normally think about gravity as, oh yeah, we're on Earth, you know, we're not floating into outer space because the Earth holds us down. An apple falling from a tree is gonna fall down. When we throw a baseball, we know it's not gonna just go out to outer space. It's gonna fall back down to the ground and bounce and come to a stop. But gravity is between any two objects. The Earth and the Sun experience gravity and are attracted to one another. The Earth and the Moon are very massive objects and they're attracted to each other. But much smaller objects, like me and you, even though you might be miles away from where I'm doing this lecture right now, there is a very small, slight gravitational force between us, okay? It's so slight that it can barely be measured, okay? It would be extremely hard to do that measurement. Okay, so keep in mind that it has to do with the mass of any two objects, okay? So the universal law of gravitation is kind of like a wordy statement here. Every object in the universe is attracted to every other object with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distances between them. Sometimes we have a formula for this, okay? Capital G so M1, M2 are two different objects and they're separated by a distance between them squared, okay? So let me draw some pictures and stuff to explain this mathematical equation. Some students can look at this really well and see, oh yeah, that makes sense. But let me break it down with some art, okay? First thing is if two objects are closer, they experience more force. Closer objects experience more gravitational force. So if I have one object here, and I have, let me do this with two different drawings here. I'll just split it up this way. So if I have one object here and another object far away, and I have one object here and another object closer, okay? The distance is described as, you know, the distance between the centers. So this distance is short or small, maybe it's 10 miles or something. And this distance is quite large. Maybe that distance is going to be 40 miles or 50 miles or something like that. So this distance is longer. The shorter the distance, the greater the force. I basically say it here, right? Greater force if they're closer. the first thing you need to recognize. You know, for example, if we have a sun, and then we have Mercury, Venus, Earth right here, right? Mars over here. Okay. We know that, so this is the relative positioning of the planets. It's not to scale, but the Earth is closer to the sun compared to Mars, which is further from the sun. So we would expect Earth to have less gravitational pull towards the sun. Okay, the sun is an object, right? Every object in the universe will be attracted to every other object, but it's related to the distance. Okay, Earth is closer to the sun, so the sun is pulling on the Earth more than Mars, which is farther away. Okay, and this has to do with the orbits. Okay, we know that Earth orbits the sun every 365 days or so. Mars is going to take longer. Okay, a Martian year is going to be significantly, well, quite a bit more than 365 days. Point number 2 is that objects more massive are going to experience a greater force. So again, we'll divide the page here in half and we'll do 2 situations. I'm going to try to keep the distance between these objects the same because we're not comparing how far or close something is. We're discussing the mass, you know, how heavy these things are, okay? So if this is 10 kilograms and this is 10 kilograms, we know that there's going to be a force. And remember, for every force, there's an equal and opposite force. So this object right here is going to experience an attractive force towards that object. And this object right here is going to experience an equal and opposite force towards the other object going in that direction, okay? And remember, forces are vectors. They have a direction, okay, as we've been pointing with the arrows, and they also have magnitude, okay? An arrow that's this long is a certain strength, and if we draw the arrow longer, it means it's a bigger force, right? It's a larger force. So over here, I'm gonna do 20 kilogram objects, okay? 20 kilograms, 20 kilograms, okay? No difference here. Both of these objects are going to be attracted to each other, but since they have a greater mass, they're going to have a greater force. I'm going to illustrate that by using arrows as before, but I'm going to show them a little bit longer, okay? A little bit longer. Now, for every force, there's an equal and opposite force. So, if you know, so you need to be thinking about this, right? The Earth is attracting this pen to the ground through gravity. The pen has a very, very small mass. It is attracting the Earth towards it as well, but this pen is so light compared to the mass of the whole Earth, so that force is almost zero, okay? If you have 2 equal masses, the force is going to be equal and opposite, okay? Equal and opposite. And here it's equal as well, so it's equal and opposite, okay? So let's put the clip notes down here. Smaller mass, less force, larger mass, larger force. Okay, smaller mass, smaller force, larger mass, larger force. How about this situation? say you have a lot of money to spend and you want to run an experiment. This is not to scale, okay? The moon is going to be 30 Earth diameters away from this. It's off the screen, but I'm going to draw a little ball here anyway and call this the moon, okay? Now that's about 250,000 miles, 250,000 miles or so. So let's say halfway in between these two, right about here, there's a rocket. It's a dot on this diagram because you can't see it. It's too small, right? Compared to the size of Earth and the moon. Where will this rocket go? We know that every object in the universe is attracted to every other object. So this this rocket is attracted to Earth because it has mass. The rocket is attracted to the moon because it has mass. But the Earth has a greater mass, right, than the moon. The Earth is bigger and it also has a larger mass than the moon. So the rocket is going to be more strongly attracted to the Earth compared to the moon. So if all of these objects were just not in motion or whatever, just ignore all kinds of orbits and stuff, this rocket would be moving towards the Earth and eventually crash into the Earth rather than moving to the moon and crash into the moon. Okay, that's if it's equidistant, okay? So rocket in the middle. It's going to be more attracted toward the more massive Earth. I'm going to draw an arrow like that to the left. So this arrow to the left is just showing the force on the rocket that is caused by the Earth's gravitational pull. Okay, that's the arrow. It's a force in that direction. Compared to the attraction to the moon, less massive moon, which is that direction. In this drawing, the Earth is opposite the line of sight here. Okay, but since the mass of the moon is smaller, the force towards the moon is going to be smaller, so I'm going to indicate that with like a smaller yellow arrow. Okay. Now remember that forces are additive, and we use the little addition techniques for our arrows, and we see that the rocket is somewhat counteracted by the yellow force right towards the moon compared to the blue, colored arrow force from the Earth. So the net effect is going to be slightly smaller. Okay, slightly smaller. Now, if you had a situation like this, where you had a large sun and then a large, a star or whatever with the same masses, and you had an object right in the middle, let's just call it a planet or something. This planet would be stable because it would not be attracted to, preferentially to one star or the other. There would be a force on the planet towards that star because it has the same mass as the force on the planet from this star. Okay, so if these stars have the same mass, and this planet is in the middle, it's being pulled apart, it's being drawn and quartered, so to speak, by these two stars that are tugging on it with equal force. So that planet doesn't, preferentially go to this star or preferentially go to that star. It could be in the middle. So it's fun to think about these types of things. You wonder if, astronomers will someday observe some kind of stable system like that, where you have two stars and a planet kind of just stuck in the middle, being roasted by these two stars. let's talk about orbits really quickly. I'm not sure how well I can explain this because we skipped the section on circular motion. But let me just give you a brief kind of overview of how this works. So if we have the Earth right here, and we have a satellite, let me just draw a little cartoon here. As we draw in the cartoons that you watch, or yeah, that's kind of like a satellite there. Okay, I'll label this in case you can't really figure out what the heck that thing is. So, okay, so first of all, because of gravity, this satellite is attracted to the Earth. So if we took a satellite and above Virginia, we took it right out to outer space, straight up, and we let go of it, it would fall to the Earth and pass through the Earth's atmosphere and burn up and disintegrate or smash into the ground. But what we have is the satellite is in horizontal motion at the same time. Remember that previous diagram where I showed the bow and arrow? Somebody shooting an arrow with the bow, and the arrow is flying through the air, and due to gravity, it is attracted to Earth. Okay. So what you have is a person on the surface of the Earth, and they shoot an arrow, and it slowly follows the contour of the Earth but hits the ground. Imagine somebody firing a rocket, okay, or a shell from a battleship that can go 30 miles before it hits its target. It goes a lot further, okay, before it impacts the Earth. Of course, that's not to scale, but imagine if somebody shot an object so hard with so much velocity that it actually never hit the ground. It kept falling and falling and falling and falling and falling and falling and falling the ground, and then it bumped them from the back side of their head or their body or their tank or whatever they're shooting, okay? So that's basically what's happening with the satellite. The velocity is so high. Let me change the color. I don't think you could see that well. It has a very high speed, and yes, it is always being pulled to the Earth, and it's always falling. We call that free fall, right? It's always falling and falling and falling, but because it's moving around the Earth at the same time, it never hits the ground. So we call that an orbit. Okay. So this is possible if it has sufficient horizontal velocity. And there's many different kinds of orbits around the equator, around the North Pole and the South Pole. Something like the International Space Station might be in low Earth orbit, which means if you go out each night, you can see it pass the Earth a couple times in an evening, for example, if you're in a good viewing spot. And we have geosynchronous orbit. Geosynchronous orbit is where a satellite orbits the Earth with the same time period as the Earth's rotation. So here's the Earth, and let's say we have the United States right here. Here's South America. I'm just quickly drawing this. And let's say we have a weather satellite. Now we don't want this satellite to be going around the world and imaging places off in Europe or the Mediterranean or the Indian Ocean or something like that. Let's say we want our satellite to always be over the United States, so we can take live images of the cloud coverage, rainfall, and all these other things that the satellite instruments might have. Plus, it's above us at all times, so we can receive radio communication from the satellite, updated images, all that kind of stuff, okay? So what we need to do is have that satellite orbit around the Earth at the same time period as our revolution. So the Earth rotates around its axis, as you know, about once every 24 hours. And we want the satellite to also orbit at a much further distance, right? Once every 24 hours. So that's going to be geosynchronous orbit. Okay? So that's at a sufficient distance, and this is your satellite here that's, you know, taking images of things. Geosynchronous orbit, let me see if it says this quote here. Global positioning satellites are the same way, GPS. Okay, the GPS satellites have to remain in a certain spot so that they always maintain coverage of the Earth. And you pull out your phone, for example, and you can have reception of more than 6 or 8 or 12 satellites at one time, so they can triangulate your position and figure out where you are. Geosynchronous orbit, here we go, is about 22,000 miles away. So, of course, if you take your phone and you're 22,000 miles away and you try to take a selfie, or you try to take a picture of the Earth, you're going to have just a small little dot. So, of course, these satellites have much better camera systems, so that when they take an image, they can see clouds, you know, going over the United States, and try from that information try to look at the images and figure out what the weather is going to be like. So that's a very long distance away. The International Space Station might be in low Earth orbit, which might be, you know, maybe 150 kilometers. So that's much smaller. Okay, it's very low Earth orbit. Okay, 150 is a lot less than 22,000. So this is geosynchronous orbit. I think that's all I want to talk about for gravity. Hope I didn't belabor this too much, but please like, give a thumbs up, please consider subscribing, and have a great day. This concludes the physics lecture on gravity and motion.